Hey everyone, let's take up question 2 on your homework reading, and this is the question with the energy level diagram or this graph. And this question is asking you to connect the idea of enthalpy with collision theory. So let's recap a little bit of what was on your reading and talk about that. So let's look at this graph as well. I have reactants down here. I'm going to underline them. My reactants are carbon dioxide and nitrogen monoxide. And when this reaction actually occurs, they're going to form the products over here, CO and NO2. Now, from the reading, you know that this is a little bit rare. So in chemistry, it is a little bit unlikely, or to actually have reactants forming products, you have to have two very specific things happen. So we need to have, number one, I need to have my reactants, they need to collide with each other with the correct geometry. So they have to collide with one another at the correct sort of angle. And when they do that, that will actually allow them to form products. But that's actually not enough. I need a second condition as well. So I actually need to make sure that not only are my carbon dioxide and nitrogen monoxide, not only are they colliding with each other correctly, but they also have enough energy to form products as well. And we actually call this activation energy. So if I look at my graph, my reactants, their initial energy is down here somewhere on the graph. And the way this energy level diagram is drawn, I know that the peak of my graph is my maximum energy I need. Okay, because basically if I go past this peak, I know I'm forming products. So I know that the peak of the curve from here to the initial energy of my reactants, this represents my activation energy, or EA. And I know that for this reaction, this is given to me, the activation energy for this is 361 kilojoules. 361 kilojoules. Now, let's look at how enthalpy is related to this as well. So at the end of my reaction, so if this reaction does proceed, you'll notice that carbon monoxide and nitrogen dioxide, so they're down here now, and so they've overcome this activation energy. Their actual enthalpy, the actual amount of energy absorbed by this reaction, is represented from here, from my products to my initial energy of reactants. So let me just dot this line over a little bit more. So from here to here, and I know that my delta H for this reaction, it's positive. So delta H, it's endothermic. I know that, again, this means that energy was absorbed by the entire system. This is 226 kilojoules. Okay, by the way, before we calculate what the question is asking you to do, the question says to calculate the activation energy for the reverse reaction. So before we do that, I want to indicate one more thing on this graph, and that is something called a transition state or an activated complex. So that's actually going to be up here. I'm going to call this an activated complex. An activated complex or a transition state is an intermediate molecule that forms before I get products. So before I get these guys over here, and it's usually just some sort of combination molecule of whatever my reactants were down here. So they form this temporary transition state or transition complex before they actually form products. Okay, so we're going to learn a little bit more about that in the next lesson. But for now, we can just indicate that, again, there's an activated complex up here before I get products. Okay, so what do I mean by reverse reaction and the energy I need to do that? Well, we can again analyze this graphically. My reverse reaction would actually involve me going from here, so carbon monoxide and nitrogen dioxide, so these would actually be my reactants in the reverse direction, and my products would be down here. I'll underline them again in yellow or orange here, so nitrogen monoxide and carbon dioxide. So how do I figure out my activation energy for this? Well, I mean, there is a formula on your handout, so you can definitely look at that. Delta H, you know that that'll equal EA forward minus EA reverse. But let's just look at it logically. If these are my reactants now, I'm going to be going this way, sort of backwards. My reaction progress is going to be reverse. And the activation energy, if you think about it, look at, again, where do I get to the peak or the steepest part of my curve is basically right here. So my activation energy is going to be from here, from the top of my energy hill to my reactants, to the initial energy of my reactants, which is down here. Okay, so EA in the reverse direction is, it's going to be the difference between this value and my enthalpy value here. Okay, so what is that? 361 minus 226. So that gives me an EA reverse. I'll write it over here because I'm running out of space. EA reverse is 135 kilojoules. And look at your graph. This should make a lot of sense because this is less activation energy I need going backwards. And this would actually be, think about if I'm reversing the entire thing, think about Hess's law. This would actually be exothermic, and this would actually, delta H would also reverse as well. So if I'm going backwards, I need a little bit less activation energy. And once I overcome my maximum activation energy, and once these guys collide correctly, they will form the products that I see down here. Okay, so collision theory as well as activation energy. So the geometry of how my reactants are going to collide and the energy they need to actually create products. These two factors are what determines if a reaction is even going to run. Now, if the reaction does run, then we can start looking at the other factors that affect the rate of the reaction, how fast it's going to go. Okay, those factors we talked about today, that would be concentration, that would be temperature, that would be if I have a catalyst or if I have an enzyme present as well. So all of those things can now influence the rate once the reaction actually runs.